So as you already heard, my name is Arne, and today I want to introduce you to an application of Provenance that tries to reduce the complexity of geospatial workflows to enhance the understandability of those workflows. So for all that may not know, I just want to give a short overview what Provenance is. Some people might know it as lineage as well. So generally, Provenance describes the origination history of data. And a widely known form of Provenance are actually workflows, because they essentially introduce any processes that are involved in generating a certain data item. Workflows also show the intermediate data as well as the actors that are, say, responsible for a given process inside a workflow. At least at some time those are shown as well. So the problem with workflows in general is that they are typically not standardized, but in terms of provenance, we rather want standardized provenance, and we can of course do that. And one recommendation for standardization of provenance is PROV-O, which is shorthand for PROV-ontology, and that's a recommendation from the W3C for standardizing provenance. So one thing that we can do with standardized provenance is of course that we can link multiple graphs of provenance if they share some common items, like actors that are responsible for any part of the workflow, or if they have a common data item, like one workflow generates a data and then you have another workflow which is so to say standardized provenance graph that uses that data, and then we can combine those two provenance graphs to a large one. Logically, that can lead to a problem. Provenance graphs can basically grow indefinitely large, so they can possibly get somewhat confusing. So, but let's assume we track the provenance of a given workflow according to standards. How can we use that? So most of the times people tend to store provenance because they want to have transparency in the data they produce. So the thing is that I think that if you want to make a process transparent, you also need to consider that, say, different people can understand your workflow. So sometimes you also want to showcase your workflow to non-experts. So you need probably a less detailed version of your workflow so that everyone can understand it. And sometimes you want to show it to fellow researchers in a very high detail so that you can work on this part of the workflow. So question is, how can we leverage the standardized provenance data to enhance the understandability of the origination history of geospatial data? So, and as I already said, ideally we could use levels of detail of one of the same graph. So it is a pretty intuitive concept. If you look at maps and that you can zoom in, I think that would be very nice if you could do this for any workflow. So I want to introduce you in this presentation how we can generate those levels of detail, and I want to showcase that along a use case for which I already generated those levels of detail and some coding visualizations. The workflow is taken from an ArcGIS tutorial which is pretty old, and it aims to find suitable habitats for a bird which is called gnatcatcher. And what we see here is the lowest level of detail of this workflow, which essentially consists of only one process, which is called intersect. And we have 4 data sets in the left that go into this operation. And the data sets are intersected, and at the end we find the potential habitats of the bird. In the purple color we also see parameters that are controlling the intersect operation. Of course, in reality, this workflow consists of some more processes. So if we go up into detail, we see some more pre-processing steps. So for example, if we look at top left, we see an arrays operation. So actually the roads data set we have on the left gets subtracted from the vegetation data set, so that we get a vegetation minus roads data set that we then intersect with the other ones. And we also see at the bottom that we use the DEM to generate a slope data set, as well as we can select suitable heights for the bird. So this is a mid-level level of detail, and if we go to the actual workflow, we see that it is somewhat larger, and I even needed to put a break into the graph because it didn't fit on the screen. So yeah, that can pose a problem because it's not so intuitive if the whole workflow breaks at the half. So what we have here is that I take my mouse. I think you can read it. We don't have this problem today. So at the bottom, we have 3 more post-processing steps after the intersect. And I also want to give some emphasis on the top here. At this point, we have a buffer operation that we apply to the roads data set. And the roads are getting buffered by 20 meters. So that is essentially the point where I want to tie this presentation to the whole sensor theme of this conference, because those parameter of 20 meters is something that could easily be derived by some in situ measurements. And that would be a little workflow on its own that we could link into this workflow if the provenance of is standardized, of course. So yeah, but back to topic. Essential question is how do we get from this high detail to the low detail? So in this case, from the left to the right. And the answer is that we want to run a generalization algorithm that is based on the process significance. And if we have the significance established, we can search for neighbors in our workflow, neighboring processes that are suitable for merging, and then stepwise merge the process into lower levels of detail. So, but of course, first we need to calculate the significance of each process in some way. And I do it with a 2-pronged approach. So at one hand, we analyze the graph patterns around each process, and on the other hand, we tag the processes with geospatial categories that belong to the operation. So let's start by introducing the left part, the graph pattern analysis. And if we analyze the graph patterns for each process, we find an individual process complexity. This complexity is essentially built up out of 3 parts, and this is the input data, the output data, and the parameters that are used by the process. So if we go to the next slide, we see an example. So we have a process in the middle, and this example process has 2 input data, 3 parameters, and 1 output data, and we can calculate the complexity of this process by 2 plus 3 plus 1, which equals 6. So if this calculation is not very complex, but if we introduce further patterns at this part, like the actors or something that is responsible for this process, or if we change up the calculation, this whole thing can get more complex than this calculation that I showed. But for this example that I show, we stay with the rather simple calculation of the complexity because it also works pretty well, as we will see. So after we established an individual complexity value for each process, we go ahead and need to take each process with a category. And then if we have a geospatial category assigned to each process, we we can match those categories to a hierarchy which consists of 3 levels. And I call this levels prepare, analyze, and model, where model is the highest level of the hierarchy. At this slide, we again see those 3 levels. So we have prepare, analyze, and model. And below the levels, we find the categories that we use to tag our processes. And the first 2 groups are, so prepare and analyze. Any category below here is derived from Albrecht. And those categories are laid out in a way so that we can basically take any geospatial operation and match it to one of those categories. And the last category, model, is there to account for any black box models or neural networks that we can't break down into smaller parts. So if we tag every process, we can assign one of those values based on the category. And the values at the bottom, they serve as multipliers. So that if we take our individual process complexity, we multiply it with the hierarchy level of the process that is assigned to, and then find the complexity for every significance for every process in the workflow. So now we have this formula to calculate the significance. We do that for every process in our workflow and can start the generalization. So what we see here is the whole workflow again to find the suitable habitats for the net catcher. And we have every process shown as a diamond shape, and the intermediate data and the parameters are depicted smaller and with only yellow and in white color because I don't want them to interfere with the processes. For every process, I noted the calculated significance at the bottom. So for example, we have the intersect, which has 4 input data sets, 1 output, and 0 parameters, which gives a complexity of 5. And intersect belongs to the category of map overlay, which has the multiplier 2, so we get a value of 10. And to start our generalization, we now look at the distribution of significance values and build classes from this distribution. To build those classes, we use the head-tail classification algorithm. If we apply that to this distribution of numbers, we find our class breaks at 3.9 and 6.7. And after we assign those classes, we start merging our processes. And the first step is that we search for chains of processes that belong to the same class. So in this case, we would find dissolve, multipart to single part, and select habitat, which are all class 1 processes, and they come after each other. So after we find such a chain, we start merging these 3 processes to a new one, and the new process gets the name of the sub-process with the highest significance. So in this case, this would be either dissolve or select habitat. And if this is equal, we select the process that was run last. So our new process will be called select habitat, which we see here. And we also calculate a new significance. So because the thing has 1 input and 1 output, which I didn't depict here, and 2 parameters, we get a complexity of 4, and a selection belongs to the level 1. So we have a multiplier of 1, and yeah, therefore we get a significance of 4. And now we go ahead and search for more chains in the graph, which are not present. So if we don't find any chains, we search for single processes with suitable neighbors for merging. A suitable neighbor in this case is a neighbor where the pair of the processes don't belong to a junction pattern. I mark junction patterns in red here. This is one, and this is another one. So we basically only find 2 processes that have suitable neighbors for merging in this case. And we start with the lowest class, which is select slope and slopes. So we merge them to a new process, which we call slopes. because slope was the highest significant start process. The new significance is 6. Then we don't find a process belonging to the lowest class. Therefore, we increment the class and search for a process with a suitable name of class 2, which in this case is the process here, select habitat, and its neighbors intersect. And we merge them and find, okay, the new process is named intersect again, and the new significance is 14. We now don't find any chains, and we also do not find any process pairs that are able to merge. So we start merging our junction patterns, and we start by merging the inner junction. So in this case, this is buffer, select vegetation, and erase. Just 3 processes that in the next step are getting merged to a new process, which is called erase again, and it has a significance of 10. And now in the last step, only this junction pattern is left, which we finally merge and land with a single process left in the graph, which is called intersect. It has 7 parameters, 4 input parameters, 4 input data sets, and 1 output data set. And the generalization algorithm stops because there's only 1 process left. So yeah, that's it from me. Thank you.
Great, thank you, Arne, for this impressive presentation of provenance and graph work. I have to be honest, I'm not too much into this kind of work, but it looked very, very interesting. So are there any questions from the audience? Otherwise, I would have 1 or 2. Jan, could you unmute the participants? And if you want or allow the unmute, I think Nick has a question. Nick, go please ahead.
Yeah, it was the slide about the process complexity slide.
Yeah.
Sorry, it wasn't numbered. I think it was maybe about halfway through.
Yeah. Let's go back. So here we are.
This one. Yeah, this one. I'm trying to understand the direction of the arrows.
Ah, yeah, sorry.
It looks like the arrows need to be going the other way, but I guess there's a reason for that.
Yeah, this has a reason, and I hadn't really the time to tell you. So I need to go further to some more slides. This has to do with the PROV-O model, which I introduced at the beginning of the talk, which is called the PROV ontology. The arrows are typically begin at the data set that was generated last, because in this case we want to have the provenance of the output data, and therefore we start with the output data and ask, okay, by which process the output data was generated, and so we go output data was generated by a process. And the process used. So, okay, this is the PROV-O model, just that does the arrows in this rather unintuitive direction.
Okay, no, it's clear enough. Thanks.
Yeah. Okay.
So it's basically the process was run, and after that we want to check how it was generated or what process steps were executed, and then we simply go the other way around. Something like that.
Yeah.
Okay. I have one more question regarding the encoding. You talked about the PROV-O model. I used to work on lineage data a few years back, and I used ISO metadata for that, and it was a mess because it created megabytes of XML. Is the PROV-O model more efficient in this way?
Yeah, it's based on RDF most part. So we go into linked data. And yeah, I think it is, but as you know, it can grow really large as well. So yeah.
In any case, somehow you need to store that information.
Yeah, that's the thing. That was the whole point. I started working on it because I thought, yeah, this is just a mess. It's just so many data, and no one has an overview about it.
And one final question. You do this auto naming of your merging process. Did you ask some users on the naming scheme about that? Because if I see something called intersection, it's probably, for me, it's easy to understand what intersection is on a geometry basis, but it's probably not that what you're doing in that process, right?
No, it's a geospatial intersection, so or a spatial intersection. No, I didn't do that, but it's really a thing which we should do in the future. Also, if I merge a process and just take one of the sub-processes and take its name, it's perfect as well. So
okay, nice.
Yeah.
Great. Thanks again, Arne, for this presentation.